And
second speaker is Professor Heipke from University of Hannover. The title of his presentation is Semi-Automatic Quality Control of Topographic Datasets, which is one of the most actual practical problem in our profession. So, Professor, please, your presentation.
Am I going to?
Yes.
Okay. Good morning. Thanks very much for inviting me to talk to you today about a topic which was mentioned a few times already, at least implicitly it was. We just heard about change in Sochi, and that's, of course, part of what I have to say. We heard about the quality and the precision of what we call photogrammetric data, and so that is part of what I have to report to you as well. And then there's, of course, mapping and geospatial, and as we heard, that's basically the same thing, at least if we take the English meaning of the word mapping. Anyhow, if I get this thing to work, yes. First of all, I bring greetings from ISPRS. ISPRS has been mentioned a few times. So greetings from our president, Chen Jun, who is unfortunately unable to come here, and he's asked me to at least extend those greetings to the 13th RACORS conference. What I'll be talking about is a short introduction. I'll give you some ideas about quality control. I'll of course show you a case study, and then I'll conclude. And there's going to be more context to the other talks as well. So change. As I mentioned, we heard about change already, and there is just a few examples of where there is change. Of course, there is change when construction work is going on. We heard about photogrammetry basically meaning to record, interpret, and measure the environment. And that's, of course, a lot more than topography itself. So there is change in urban sprawl all over the world. I'll take the example of Rio. There is, of course, natural change. This is an island off the coast of Germany, and you can see that the coastline, in fact, has changed considerably over some 50 or so years. There is change, of course, also in the Arctic and the Antarctic areas. Here you see the retreat of a glacier in Greenland, and again, of course, photogrammetry and remote sensing is more than just topography. Environmental monitoring is just an example here. There is change in height. In this case, an example from INSAR measurements off the coast of Italy. And so change needs to be captured. I say that because there is, of course, a focus on mapping, but mapping needs to be up to date. And therefore, then, there is the task of repeatedly look at these changes. So what I'll talk about in more detail is a system where you can see whether your geodatabase, which you have captured some time ago, is actually still up to date. So there's a comparison then between what you already have in your database and what's the situation as presented in an orthophoto, as we'll see in a minute, at a later stage. Change, of course, comes in different rates. Therefore, we look at different update cycles, and there is discussion about whether it should be a type of periodic or rather a continuous change. If you think about car navigation system, you really want the new road which was opened yesterday in your data today. So that's what I would call a continuous change, a continuous update, and it's being done through the users. Crowdsourcing was being mentioned earlier as well. By users, car drivers, of course, uploading the data of their tracks basically at night, so it's available to everybody the next day. So there is a need for GIS update. This is basically what I'm trying to say. Now, there is also a need for quality control in other parts, and I'll just have a few examples, and I'm sure you basically know what I'm talking about, where there is, for instance, parts of that area here simply being labeled incorrectly. I have a mouse here, so should work, yeah. This part here, of course, is labeled as built up, and as you can see, it's not. So that's maybe just an error from the operator. And here's, of course, a house which is missing, which is labeled as grassland. There is the area which is labeled as built up. Another example you're seeing here, whether you simply have a geometric problem, the road in the database is not where the road should be, as you can see it, of course, when comparing to the orthophoto. Or here's another one, a typical redevelopment area where, as you can see, lots of what is labeled in the database as grassland is in fact been developed and now should actually be labeled as built-up area. So the question is, given such a situation, can you come up with an automatic method to actually at least indicate to the operator that something is wrong? And if you get it, if you take it even further, you also want to correct it automatically. But our aim then is to basically compare the database or the contents of the database with an actual, with a current orthophoto, which, and I call that reality without wanting to go into the philosophical implications of what reality is. The underlying point here is, of course, automation, and then, therefore, again, in productivity. So what I'll report to you is a case study where we have implemented these ideas in a cooperation with the Federal Agency for Cartography and Geodesy in Germany. We've developed a prototype software which is basically running at BKG, which is semi-automatic. You'll see that the overall control stays, of course, with the operator, with the human operator. So it's a help to the human operator to speed up the process. It uses regularly available data, so that, of course, has to be seen in the background of the German scenario, where we have regular coverage of orthophotos. And the goal which was set for us was a productivity gain of a factor of 2. So the workflow, you have the orthophoto, generated according to all what we know, and you have the geodatabase. And first, you do an automatic image analysis, of course, processing the orthophoto with the help of the geodatabase. And for each and every object of the database, you come up with a decision, really. Either the two data sources are basically the same, so you do find in the recent photo what you should see, namely what you have in the database, or you don't, in which case you have this red light. And it's the red light then which will be which triggers visualization, and this is where the human operator comes in to then take a decision as to whether any action has to be taken. Okay? Here is a very short view on the system components. It's basically a black box system hooked onto a GIS front end. So the GIS front end basically initializes the process and does the interactive processing as soon as the operator is called upon. And the backup system is divided into what we call a knowledge system, which is basically a representation of the object and of the feature catalog and the actual image analysis. And I'll slowly take you through some of these steps here. For instance, you see the knowledge-based component. We work on a semantic network here to represent the hierarchy of the individual of the GI catalog, of the individual object classes, of course, where we basically have to map, as I say, the GI catalog onto some kind of computer-readable representation. The links basically only connect, as you can see, a region can be agricultural, it can be inhabited, and inhabited areas can then be industry and settlement, and so forth. We have a user interface. I'm not going to talk too much about it, which comes at different levels of resolution, that is. And of course, that is where you would interact with the system. As far as the image analysis component is concerned, we subdivide into area, lines, and in particular roads. So there's of course a set of algorithms which if you've done computer processing or image processing for some time, which may sound familiar, such as texture analysis or edge extraction or line extraction, etc. And I'll show you some examples of that, where, first of all, I'd like you to look at this one, where you can see that industry blocks or industrial areas and settlements, human settlement, basically have a different scale, and therefore then you can use that scale to use different texture analysis to differentiate those two classes, which are of course both part of the settlement area. So hierarchical texture analysis is what we use here, and here's an example where that input image shown at the upper left is actually classified using what's called a Markov random field, and I'm not going to go into details about MRFs unless you want me to. Do ask. And a classification step where the training data are provided by the geodatabase. So there is no need to come up manually with training data. That's one of the advantages, of course, we have. We do that in different resolutions, as you saw, because these objects have different characteristics at different resolutions, and we basically then overlay these individual results at the individual resolution levels to come up with the result, so that I showed you this example beforehand. We can now compare basically what the results of the images are to the left, and the GIS is of course having a different set of classes. This is the classes we aim at, so there needs to be some mapping going on. If you have, say, 15 houses on a parcel, well, probably it's not a parcel anymore. That type of rule is coming up here, and you would then come up with a result like this, where these are the areas which need to be looked at by the human operator. And you can see these are the ones where grassland came with a lot of houses, for instance, which is of course not something we want to see. We use a similar concept with line processing. We know where to look for lines, where lines are of course roads more than anything else, because roads are the most important class of linear features, at least in Germany. So basically what we do, we pick out a line from the database and we mask that area in the image, and we do dedicated processing at that particular area, which you see in the figure B here. And if there is enough support for a line to show up, as you can see in D, then we'll color that line in green and say, okay, that line which is available in the database is also available in reality. So that's the basic idea. We do that in a twofold system. The first result, where we look at individual objects only, is depicted to the right, and what you see is a lot of red. So that's not a very, very good result. But then if you think about roads, they are being built to connect places. So connectivity or topology is something which we use in that second phase. And then we come up with what you see at the right there, which basically in the rural areas, as the rule of thumb result tells us that we can get 2/3 of the roads and verify, check them automatically. There is more examples here. I'll speed up a little bit because maybe I have to.
Speed up.
Okay. This is just to show you that no, it's not that one image which we used our algorithms and it does work, but it's quite an extensive number of images which we have been processing so far. Okay, so we can differentiate automatically different classes of area objects. We can check road data, linear object, question of course, okay, and how good is it? So we extensively checked the algorithm, or the system rather, as I mentioned before, using this confusion table, which some of you may know from classification approaches. Basically, we have the system to say green, red, and then we have an independent reference that is a human operator to say correct and incorrect. Now, out of these 4 tables, the one thing you don't want to get is undetected error. The system accepts a result which in fact is incorrect. Why? Because that type of error would simply stick in the database, and this is exactly what you want to avoid. So when I show you these tables then, the entry to the lower left should be small. That's basically what I'm trying to say. The more you get on efficiency, the more you get green in both cases. The system agrees with the operator, no need for further checking. That is the efficiency gain you're getting. And the 2 numbers, the 2 entries at the right, of course, will mean that the human operator is called in and has to take a decision himself. So briefly showing you results from IKONOS scenes, so high-resolution satellite imageries for area objects and for road objects. The basic message here is that about 2/3 are in the green field. Right? You see 70% and 62%, and the one below is rather small. So that was the aim. And there's, of course, a compromise which needs to be reached. Now, we've tested this system in North Africa with more or less pretty similar results. And I'm not going to go into discussing these details. And we've also, of course, used aerial images with a resolution 3 times as good. And again, the results overall are pretty much the same thing. Now, when you looked at these results, I already mentioned that, it is clear that the productivity factor is about 3. Well, that's because 2/3 of the objects were checked automatically. It's only 1/3 which you need to look at as a human operator. That's where your factor 3 comes from, right? And I'll see some parallelity here with Rakursk. No, we have not processed any data from Antarctica. But we have processed data from a number of countries around the world with the system, with very similar results all over. So I think this is already my last slide then. I've presented a semi-automatic approach to you for the checking, for the verification of existing geospatial databases. I think I could show you a significant gain in productivity of about a factor of 3. Our partners were happy, they wanted a factor of 2. And the decision, of course, remains with the human operator, something which I believe is very important as well, because totally autonomous solutions we don't have in our domain at the moment. It's basically a circular approach, I call it, because you link the database with new acquisition, put it in the database, come up with new acquisitions, etc. So there are cycles in terms of updating and refinement, of course. I believe it's useful for 3 different tasks. You may be interested to check your database, the quality as an internal database check. You may need to periodically update your database. That's the temporal aspect. And then, of course, you have outsourced data acquisition, and you get this bill on the table, and the question is, are you going to pay, yes or no? So you can actually check the quality of what your partner has delivered in such a way. And the approach is operational. I mentioned that it's implemented at BKG. So with that, I'll thank you for your attention. Thank you very much. Spasiba.
Thank you very much. And I have a very easy job today. Everybody is so disciplined, so we have really still time for the questions and answers. I just would like to tell that the presentation was really very interesting, and it's not a usual obligatory compliment. It was really very interesting because it's touching one of the most actual practical problems in the industry. So, вопросы?
Any questions? Was it Was it some specific software? Did you use any specific software, concrete software?
This is software developed at the institute. Yes, it is specific software.
Is it available for the commercial companies?
We are discussing with commercial companies, so we can talk about these things, yes.
And is it developed especially for the ATKIS database?
We started development for ATKIS, but the one slide which showed these countries around the world, I put this in to basically say that we can import any kind of data as long as it's GML standard in one way or another. Really, we're importing geometry and one label, road, water, terrain, etc. And so, yes, we can handle others as well.
Thank you very much. Еще вопросы?
Any other questions, comments, additions, maybe? Doesn't seem to be the case.
Or